So we covered a lot of ground today, and I'd like to make a summary slide of what we talked about. How to find the DTFT, x of e to the j omega, this continuously variable frequency domain function. And the other one is how to find the DFT, this discrete frequency domain sequence. So the first way we talked about to find the DTFT is just intuitively, look at the sequence. If you see something that looks like this, that's constantly changing directions, it's got a lot of high frequency. If it's something that's mostly staying constant, give or take, it's got a lot of low frequency. We talked about how to find it analytically, though. And analytically, it means exactly. That's this summation of n equals 0 all the way up to capital N minus 1 of x of n times e to the minus j omega. And that will give us the exact DTFT. We talked about how to find it computationally. And that's using the FFT algorithm, but zero padding the living daylights out of it. So even though the FFT actually strictly finds the DFT, not the DTFT, if we give it our sequence and we zero pad it big time, and we zero pad it in such a way that it's a factor of 2. So here's an example of zero padding it quite a bit. That'll be a good approximation. Of course, the indexing will be wrong. The indexing here will go between 0 and it'll be a sequence out. So it'll go to 0 to 2 raised to the 30th power minus 1. And you'll have to plot that not between 0 to 2 to the 30th power minus 1, but between 0 and something just barely less than pi, 0 to 2 pi times n minus 1 over n. But if n is 2 raised to the 30th power, this is essentially just 2 pi. And then the last is we talked about how to compute it from the discrete sequence DFT. And that's that double summation sequence that's in MITRA. Despite the fact that it seems amazing, it's actually very, very rarely used in practice. And that's because in practice, if you have an output signal that is not smoothly sampled, that looks like this, and if you put that signal into a speaker, that speaker's got a voice coil, and that voice coil has inertia. And that inertia is going to smooth down the response of that filter to make it smooth. If this was your signal into the motor of a robot, that robot arm and that motor has inertia, and it's not going to instantly move in jagged leaps. If it's being sampled finely enough, the inertia will just make it smoothly interpolate. So you actually rarely need to perfectly reconstruct something in a very smooth domain if you've got it sampled finely enough. Now, to find the DFT, this is what we're typically interested in. We talked about 3 ways to do that. We've talked about analytically. And so analytically, that's the equation from n equals 0 to capital N minus 1. We multiply x of n by our e to the minus j, 2 pi k little n over capital N. That's a j. And that's our analytic equation. We talked about how to find it computationally. And that's using the FFT algorithm. And then the last is you can also derive it from the DTFT by just sampling it. You take your x of e to the j omega, your DFT, and you just sample it at every omega equals 2 pi k over n for k equals 0. Let me write that more neatly. For k equals 0, 1, and so on, all the way up to capital N minus 1. All right, that's this lesson in a nutshell.